that connection, unfortunately, it still doesn't work. So we have to make do with this. Okay, any further questions to the instruction.e file? Yes?
How can you choose to extend the file rather than just declaring the method inside the struct?
Say again?
Sorry, couldn't you have just declared the check response method inside the struct, or do you need to extend it?
I don't need to extend it. I just wanted to show you how to extend something. And that is one way of doing it. But yes, I could have just put that in here. I could have just said, when at, then do this. I could put that in there verbatim. You can try that out. You can take this off, and you can just copy and paste that in there, and it's the same. Yeah. Any other questions on this piece of code? Does it look intuitive? Does it look doable? Yeah. So the next one is the driver, right? So this is where we're going to generate our data. Now we need to figure out how we're going to get that into the design. So find the driver, and I do that here. So the driver is a unit because it's a static part of our test bench that wires our E-code to the design and the verification. And so it is not surprising that it has a very standard piece of code at the top to declare ports for each input-output of the design and the verification, right? So a clock port is an input-output port. It's a simple port. It's taking bits. And this is the syntax that has to be used, right? It was much simpler. Previously, you just had this plus this string. Later on, they rewrote it like this. So that is why you are given this, because it would be unfair to make you figure this out. This can be driven or read by the Speckman environment, and it is constrained so that the clock port HDL path is this path in the HDL. So it's often from the module calculator1_sn, the C clock. And there will be a C clock signal in the Verilog code under that name. The reset port in my E code is constrained to be wired to the reset signal in the Verilog. Command in, the command in port, well, in my case, my test bench only covers the first port. Okay? So I've got a command in, a data in, a response one, and a data one. And so I'm wiring the command in to the request command for the first port, and I'm wiring the data in to the request one data in signal in the Verilog. So these brown ones are all Verilog signals, and you can see I'm using a string to connect it. And on the other side, I've got something underscore port to tell me that this is actually a port to the design. And all the input outputs of the design I can wire like this. So your driver, I would expect. Your driver, I would expect to aha, there it is, a secret one. Let's get one down here. There's a secret one down there. Let's hope this works. That would be brilliant. So your driver would have to wire all the other ports up as well, right? So the second port, the third, and the fourth. This wiring is only for the first. Does that make sense?
Yes.
Yeah. And it's literally just this string, and then on the other side you have to have the underscore port, which is a convention to tell us which signals are effectively hardware signals, right? For which we have complementing variables. But you can see that they don't have to match the string, right? So here I've got the request one data in, and here I've got that as well. But where have I got? Do I request one command in, request one command import, request one data in, request one. So I have made the match, but I don't think you have to. Okay? So now that we've wired it up, I need to know which instructions I want to drive, right? And in order to declare which instructions I want to drive, to have a data type, I'm saying there is a sequence of instructions for which I use the list type, right? So there's a list of the instruction structs which we've just looked at in the instruction.e file, right? So I'm declaring a list of type instruction struct. And I'm also declaring an event clock, which is the falling edge of the clock in the design. And I'm also declaring an event response, which is any change of the out response port of the design. Yeah? That's how you refer to a port. As part of the calling of the fall and change, that's part of the syntax when you define events like this. Okay, so you can see here as well that it's part of the port syntax. There.
So do you just always suffix ports and polls that uses?
It's a peculiar syntax in the same way as every statement has to have a semicolon at the end, even if it's not intuitive. This is how the syntax is. That is why you're being given this, because it would be hard to find out yourself. Okay, so now let's see. If we do a very simple drive of the reset, that doesn't take any input, and I'm counting how often I do it, then I've got a loop that tells me how often I want to drive the reset. I've got reset on all reset bits, and then I'm driving the reset port of this width. I wait a cycle, and I do this as often as specified in this loop. And then I'm pulling the reset low again. Okay? So driving the reset seems to be quite simple, and that's the first method that we have, which is the time-consuming method. So it does that for each clock cycle. And it basically, each clock cycle, sets or drives the reset port, so it actually gives data to the hardware signal, pulling it up, and then after doing this for 8 times, resetting it back to 0, taking the reset back. Does that make sense? That is probably the simplest we see. Okay, let's have a look. Now, if we wanted to drive real instructions, we only need to do a little more. The reset is a simple one. Now, if we want to drive instructions, remember we have a list of instructions, which is our instruction sequence. And so if I want to drive an instruction, then I give my drive instruction. I will try it out just before. So what? This is going to be risky because it may just. So on the assumption that the cable is alright and my adapter is alright.
Yeah, but your adapter's registered, isn't it? That cable's fine. Just test it, it's working fine.
I switched this off.